The quiz is open. The assignment from yesterday is open. I know we did not get time to really do that in class, and so it is open today. They're both very short, 5 questions for the assignment, 6 questions for the quiz. Remember that the quiz is in quiz mode, so you will not get that 4th guess. So take your time on it. And just real quick, what I would like to do is go over, if I can get this to work properly. There we are. Go over the study sheet. So remember that these study sheets are on Sapling. All you have to do is scroll down into the chapter and find the study sheet closest to the assignment. So we're starting chapter 8. If you want to find this, just scroll down into chapter 8 and it'll be the first study sheet you see. I just want to go over the big points from yesterday. So remember, we're talking about kinetic molecular theory. It's the theory of the movement of molecules. And the first thing you want to remember is they're always moving. They don't ever stop moving, especially when you talk about a gas. A gas, molecules of a gas will just forever bounce around their container until the end of time. They're never going to stop bouncing. They're never just going to fall to the bottom. They're just going to keep bouncing around. And so that's one thing to remember. Even in solids, where my molecules can't move past each other or switch places, they're still moving. They're vibrating in place, and that's what gives them their temperature. So all molecules are always moving, unless you get down to like 0 Kelvin, which we'll talk about later. The other thing I want you to know, they go in a straight line until they hit something. So they're literally just going to go in a straight line until they bump into something, and then they're going to bump into something else, and they're always just in a straight line until they hit something, either their container or another atom inside the container. So the last thing is, not the last thing, just for this section. An elastic collision is what atoms do. Everything else will eventually slow down. Like if I throw a tennis ball against the wall, whatever the speed is going in, once it hits the wall, it's going to slow down. It's going to leave the wall with less energy. Atoms won't do that. If an atom comes in at 5 miles an hour and hits the wall, it's going to bounce off at 5 miles an hour and it's going to leave just as fast. Elastic collisions mean they don't lose any energy when they bump into stuff. They just keep going. So they will literally bounce around this beaker forever as long as the lid's on and they're still in gas form. You will not really use this. They do ask a question about this. We're not really going to use this formula. I'm going to show y'all later today what the formulas we're going to use are. Remember that temperature is your kinetic energy. So the more kinetic energy I have, the higher my temperature. I'm going to be very hot. The less kinetic energy I have, the lower my temperature. What else do we have? Remember that your big molecules or atoms will be slower. The bigger things are slower, the lighter things are faster. And we saw that yesterday with the helium versus the sulfur hexafluoride. Helium's very light. It moves very fast. It makes my voice higher. Sulfur hexafluoride is heavier. It moves slower. And when it comes out and my voice comes out through it, it's a lower register. Let's see. And then the last thing, they talk about gases a little bit. The thing to remember about gases is they don't clump up. The atoms will not stick together or be like in a clump or a ball. They're always bouncing, always moving. There's a lot of atoms in a gas. So like how many atoms of air are in this balloon? A whole lot, like more than you could ever count in your lifetime. That being said, there's a lot of empty space in between them. So I have a lot of really tiny atoms with a lot of empty space in between those. So they're very far apart. They're always moving, always bouncing, just moving around their container. And, the diffuse part. Diffuse means that like when I spray some perfume over here or cologne, eventually, not immediately, but eventually you're all going to smell it in the classroom because those atoms are literally just going to randomly bounce around the classroom until they spread out everywhere and one of them eventually goes up your nose and you smell the perfume of the cologne. So use this today to help you do the regular assignment first. If you haven't done that yet, then go ahead and do the quiz. Remember that it's in quiz mode. And I know it won't take y'all that long, so I'll give y'all a little while, and then I'm going to talk about what we're going to do next week. We're going to kind of introduce a couple things and talk about that. So if you have any questions on the quiz, let me know, and I'll be right around. And if you're watching this at home, give me just a second, and the video will start again, and I'll do a little lecture. All right, so what we're going to do right now is just kind of introduce what's coming up in the next section. Because technically, even though it's Friday, we're at the beginning of a brand new 6 weeks, and we're going to start some new stuff. Now, stoichiometry is tough, and this is going to be easier, but don't take that as easy. It's still going to require some work. But if you hit this hard and we get through these assignments, you should be able to pad your grade a little bit and make sure you're well above that 70 comfort level. So if we come down here to chapter 8, which is where we're at now, just a quick little reminder, these are your study sheets. It says study sheet, so you go down in the chapter and you can find your study sheets there. We're done with section 8.1. It's just one assignment and one quiz. We're moving on. 8.2 is where we will stay for a little while. What we're going into now is gas laws. And obviously gas laws talk about gases, so I've got balloons over there. We're going to talk about gases and the problems with those. These are a lot of assignments before we get to our next quiz. It's a lot of daily assignments, and they're all just a little bit different. And the bad news is every single one of these assignments has a different, unique formula that you have to use. The fact that they're all different is kind of bad, but the good news is, A, it's a formula, so you don't have to create stoichiometry problems from scratch every single time. You actually already know what your multiplication and division needs to be. All you have to do is find the numbers in the problem, plug them in, and get your answer at the end. So in general, compared to stoichiometry, even if the formulas are a little tough, formula work is usually a lot easier. Now, we will go through a lot of gas laws. We're going to start Monday with Boyle's law. You go to Gay-Lussac's law, Charles's law, Avogadro's law, the combined gas law, the ideal gas law, and then at the end, to throw in a little bit of extra work, Dalton's law of partial pressures. And when we're done with all those, we will take the gas laws quiz at the end. So there's a lot to go through, and what I'd like to do today is spend just a little time going over the overarching thing. Because one of the things I kind of dislike about this, there's not a better way to do it. This is a good setup. But we're going to start doing these problems, and it's not until the end that you really get to see how all of these are interconnected. And so I'm going to try to show you that today, and hopefully over and over again as we go through these assignments, so you kind of always keep an idea of how all this stuff is going to be connected in the long run. And I think that makes it a lot easier, or at least it always did for me. So today what I would like to do, I'm going to turn the lights on, so shield your eyes. We're going to come over here and do a little talking and a little board work. And we're going to think about gases and what our problems are going to be with gases. So give me just a second to come over here and marker this. Wonderful. I'll take a purple with me too. Gotta have some color in your life. Color's wonderful. Let's see. My balloon that I blew up earlier. I got a weird bag of balloons from the dollar store. So I think this is like a clown balloon where you do the animals, but the clowns blow them up with their mouth, right? They do the stretchy thing. They always have the stretch that they do. Y'all know what I'm talking about, right? And then they blow them up. This, I can't get it. I don't know that it's a real functioning balloon. It just, and it doesn't expand. So someone was like, you got to stretch it, but you can stretch it this way, but you can't stretch it that way. Oh, did I just tear a hole in it? No. Yeah, I am. I understand how balloons work. I got this one fine myself without any instructions or anything. So we have a balloon here. For the people at home, just a regular balloon. Let's say we're in a lab and I give you a balloon and I tell you to take some readings take some measurements on this balloon. What can you measure from this balloon? What are some things you could get from this? The width of it. So already we start to get into size. Now, the width and the length are going to be hard to calculate. What's another size thing I can try to get from this balloon? What's another way to say size besides width or length? What What I do with size, like if it was a cube, what would I do with my length and width and height? Yeah, I would make a volume out of it. And we can talk about the volume of the balloon, right? That's essentially like the size, but it's easier because the length of the balloon, I could have a long balloon like this, but it won't have as much air in it as maybe like a smaller balloon like that. And so length is good for some things, but for round stuff and for gases, we really want to talk about volume. So volume is one thing that we can describe this balloon with. What's another thing I can describe about this balloon, or what's in the balloon, more specifically? The air. So like you said air, it could be something else in the balloon, right? I could put like hydrogen in the balloon. Right now, it just has my hot breath from my lungs, so it's like carbon dioxide and nitrogen and oxygen. But yes, the chemical formula for, that's not how you spell chemical, the chemical formula for whatever you have inside your balloon. And this is going to be a little bit separate from the other things we're going to talk about today. This will factor in. They'll always give it to you. It's not going to come into play too much until we get to some later problems, because obviously at some point they're going to be like, okay, we need to ratchet it up a little bit. And they'll start to mix some stoichiometry back in just a little bit, but not a lot. So your chemical formula is something else. I could talk about what kind of gas is in here. What else can I talk about this balloon or the gas inside of it? So we have volume. What if I squeeze the balloon? What happens? What is changing if I squeeze the balloon? What am I doing to it? What will eventually happen if I squeeze the balloon too much? It'll pop. Why? What's happening when I squeeze it? What's changing?
The air is coming more together.
Yes, it's coming more together. That's your pressure. I'm changing the pressure here. And so pressure is another thing we can describe about air. How much it's squeezed into whatever container it is. If it's not squeezed at all, it's just normal pressure that's around us. If I had to force it in there like I do with my lungs, in this one, it's pressurized. And you know that because if it was a normal balloon, I hadn't tied it off. What happens if I let go of the balloon and it's not tied? Oh, it flies away because all the air wants to rush out because it's pressurized. So pressure is another thing. What's another thing? I'm looking for two more. What's another thing I could use to describe this balloon and the air inside of it? Any guesses? What would happen to the balloon if I put it in the refrigerator? Yeah, so obviously the temperature would change. What would it look like when it got colder? Does anybody know? Yeah, it would shrivel up. It would look real small. I mean, it wouldn't go like empty, but it'd be much smaller and it would kind of be shriveled up. And so temperature is another thing that we can describe about this balloon. In fact, we'll kind of see this in a second. I'll give you a little example of how all these things can change. And then the last thing, think about this. If I do it this way. All right, I got my balloon now. What else did I just change about this balloon? Oh, is it time already?
Yeah.
Y'all left out. We'll have our balloon talk tomorrow. Oh, I was hoping it would stay further closer to me, but I gotta go. So don't worry, you're not missing anything. We will finish this talk tomorrow. Sorry, online people who stuck around for the second half of the video. You're gonna be a little disappointed, but we'll catch back up Monday. Not a big deal.